Hello, my name is Desmond Main. We're at BrooksDale International Systems in Vancouver, British Columbia to start the video documentation of an actual test of the EVACU8 emergency self-rescue respirator. It is Wednesday, March 9th, 1994. I'd like to show you the facilities and to introduce you to a few of BrooksDale's people. I'd like to introduce you to Cindy. She's the administrative assistant with BrooksDale. Chances are when you phone here, this is the lady you'll talk to.
Hello, welcome to BrooksDale.
Right now, let's go upstairs to the corporate offices and we'll introduce you to a few more BrooksDale's people. We're now in the office of Roger Killen.
Hello, I am the Chief Operating Officer of BrooksDale International Systems and have been involved with EVACU8 since its early development. Thank you for having the interest to view the material that is about to follow. BrooksDale will be truly grateful for any support you can lend in assisting us achieve our mission of reducing the incidence of deaths and injuries due to smoke inhalation.
Let's now move out and introduce you to Ewout van Dushoek, VP Business Development.
As the VP Business Development, my time is spent on strategic planning and building the company's infrastructure to ensure that it's a proper operating entity.
You meet Calvin Mall right now. Calvin's the controller. Calvin, I wonder if you could tell us what you do for BrooksDale.
Sure. My responsibility as controller of BrooksDale is to maintain the financial integrity of the company. So I get involved in things like cash flow forecasting, working capital management, budgeting, planning, things like that. So basically looking after the financial area of the company.
I'd like to introduce now Carrie Schlappner. Carrie's been with EVACU8 for about a year and is going to demonstrate the actual use of the product.
Hello.
I'd like you to meet John Swan, our president and inventor of EVACU8. John will be donning EVACU8 in a real live fire test demonstration.
Good afternoon, my name is John Swan. I'm the president of BrooksDale International Systems Inc. You're about to be introduced to BrooksDale's EVACU8, an emergency self-rescue smoke hood. Why don't we go down to production and see how it's made?
Well, that concludes our tour of BrooksDale's head office. We'll see you next at the actual live fire test at the BC Safety Training Center. Good morning. We at BrooksDale International Systems are at the BC Safety Training Center, which is the fire training grounds for the Pacific Marine Training Institute, to document an actual test of the EVACU8 smoke hood. It is Wednesday, March 16th, 1994. Behind me, you'll see the smokehouse, which will soon be filled with the deadly products of a fire. After the fire is lit, the president of BrooksDale, John Swan, will don the mask and enter the smoke for a period of 15 minutes. During this time, the levels of carbon monoxide, hydrogen cyanide, hydrogen chloride, and nitrogen oxides will be monitored before and after the test and at 5-minute intervals during the test. The chemical monitoring will be done via grab samples and passive dosy tubes. To simulate a person escaping from a fire, we'll have John walking, and he'll show himself outside the door. As well, John will complete a manual dexterity task of tying knots. The precautionary measure, we have a paramedic team, ambulance, and 3 safety men with BAs inside the building with John. Moreover, Elizabeth McDonald, occupational hygienist with BC Research, is overseeing this test. Also, we have an outside safety person and an inside safety person. Either one can call quits if there's any danger to John. As well, we have a charged hand line on the other side, set in case anything goes wrong. Extend our thanks to the BC provincial government, who under Glenn Clark have provided monetary assistance via the TAP fund. We will demonstrate in this video, under the supervision of an independent third party, that EVACU8 can save lives. Thank you very much. Let's start.
We won't go into the fires right anyways. So we'll go in and test right away.
Yes. No, only it's just the top.
We're going to take a unit at random. This is unit 24108 for use in this project.
We'll start lighting it. Once we light it, then we'll get the products up, we'll get some smoke, and then we'll get you to don it.
20%. Okay. Terrific.
Okay, John. What are you doing, John? What are you doing, John? Looking good, you're up to about 400 plus CO.
What was that about the oxygen level?
It's about 17 and a half right now.
So you're opening the door to bring the oxygen level up?
Yep.
Good.
Just over 17, so we'll leave her there.
Yeah, Laurie and Jason are doing what we call instantaneous readings. The tubes that John has on his jacket will give us a time-weighted average so that we'll know the carbon monoxide concentrations and the hydrogen cyanide concentrations that he's been exposed to over the whole length of his exposure. So we'll have now two different types of information, the sort of the instantaneous but also the time-weighted average.
Elizabeth, if he was feeling the effects now, what would he be feeling? Like, what would be his symptoms?
It would be disorientation, confusion. He wouldn't be feeling any overt health problems at the moment. But we should be starting to see him become confused, maybe staggering a little bit. So at this level of carbon monoxide, if in fact we do have around 400 parts per million, and at this level of exposure, it's starting to affect his central nervous system. It should not yet be affecting his respiratory system. But if exposure went on and if he really is exposed to 400 parts per million, for 20 minutes or so, then we might start to see some respiratory distress. If in fact he is exposed, he will end up with an almighty headache. So the carbon monoxide's around 500, which is terrific. It's just where we wanted it.
Okay. And by my watch, we started at 10:26, it's 43, so 42, so somewhere around there. You want 20 minutes? We're doing 15. 15, oh, we're finished that. 1 time. Oh, okay, well, we're out of here. Okay, let me just finish these things off. I'm going to do You want to go pretty long there? Okay, you want to go pretty long there? Okay, I'll just finish the some samples out and we're done. That's good.
Still running, Jess?
Run through, so we're going to go pretty long there until it's 21.
Still running,
Repeat back at 600 for cigar. No harm.
Okay, skipper, point to her. Point.
Okay.
Okay.
23, 45. One more minute for 20 minutes, John.
That was 20 minutes for those of you who don't live time.
As soon as you what you do is just hit what we call our safety light at 17, so we're fine. We're fine? Yeah, we're okay. That's 20 minutes now.
Okay, a lot of the,
Good stuff, okay. Everyone home?
done it?
There you go. Are you okay? Absolutely. Just sweating a bit. Pretty hot in there.
Okay.
Worked beautifully. In fact, I think I was doing better than the guys with the SCBA. Worked beautifully. To go and have my blood
Yeah, we have to, you have an appointment. Yeah, that's probably the best.
It was good. I could see quite clearly. I was very pleased with that. So, in fact, I was able to see a lot more than I anticipated.
Is that right?
Yeah.
You didn't taste anything?
No, not a
You
thing.
didn't even taste any throat.
The throat
be
got
dry.
The throat got dry.
Because of the it would be dry.
But nothing. Nothing. I felt nothing untoward.
Good.
Just that.
Well, got everything I wanted.
I've got another one.
I could have actually gone much longer, but the SCBAs are running out.
Yeah.
20 minutes.
So you said you think 20 minutes.
Well, at lab levels, where you test at the high extremes, a minimum of 15 minutes. But under real use, where your respiratory rate is generally slow, and because you're breathing across a negative pressure filter, you slow down in any case. You're obliged to. You can't breathe very fast, so it calms you down. Thank you. It lasts much longer.
How's that gonna work?
Thanks,
There you go.
Thank you.
Oh, that's great. Thank you so much. Little toesies.
What we have here is some of the equipment that we used in monitoring the fire, first of all for safety reasons, but also to find out what sort of a fire we had. This meter we were using to measure the oxygen level in the fire. If the oxygen had dropped below 17%, then we would have stopped the test. We were also using a carbon monoxide meter to keep track of the carbon monoxide concentration in John's breathing area. If the carbon monoxide level had exceeded 1,000 parts per million, again, we would have stopped the test. We also wanted to keep track of the levels during the fire. So Laurie and one of the other firefighters were pulling tubes to get instantaneous readings for gas concentrations. And this illustrates how the tube is, the air is pulled through the tube. And the tube has a color reagent in here which changes concentration if the gas is present in the air. And I don't know if you can see this one, but this is a tube for cyanide, and you can see that there is a change in the color from yellow to the pink, the reddish color, and that indicates that cyanide was present in the air, and that allows us to read the cyanide concentration at that instant that we took the sample. Also, samples were being taken for carbon monoxide, and this is a typical tube for carbon monoxide. The concentration is red where it goes from black to yellow, and so this tube tells us that we had approximately 450 parts per million of carbon monoxide when this tube was pulled. In addition, these are the dosy tubes that John was wearing, and for instance this shows that he was exposed to approximately 150 parts per million of carbon monoxide for the 20-minute period, which would translate to about 450 parts per million in an hour. So we've got different measurements of both the gases in the fire and that he was exposed to.
Very comfortable, no problem at all. Rotation now, good visibility.
We started this test for 15 minutes, as you've seen me advertise essentially for the previous segments. What we ended up with when we got in there, John was doing so well and everything was going so good that at John's request we extended the time to 20 minutes. Our carbon monoxide levels were around the 400 to 500 range for the bulk of it. Our concern was the oxygen content. We had an oxygen content at no less than 17% during the entire test. And John, I wonder if you could maybe elaborate a little more on what it was like and how the hood performed.
Well, I'd like to, Des. Thanks very much. Well, it was very comfortable inside. The hood provided appropriate protection. It allowed me to see quite clearly, carry out a number of dexterity tests in knot tying, etc. I was able to review the figures for the levels of toxic gases quite clearly. I was able to move around freely. There was no bad taste in my mouth. The product worked perfectly. I had no problems in extending the test to 20 minutes, and in fact I felt that I could have probably gone on a little longer, but however I think we've proven what we came to prove. Thank you.
Well, here we are, 2 days later. It's now March 18th. We've taken the original EVACU8 mask that we used in the test, and we've bagged it immediately after the test, and we're going to be disassembling it now. John's going to take it apart, and
right?
That's correct. See, the hood is intact. Nails around the draw tape are intact. Both sides intact. Front here intact. The wells mouthpiece, nose clipper intact. Lots of perspiration and condensation as a consequence of the sweating over the 20-minute. You can see the inlet valve here. It's intact. The exhaust valves on either side are intact, operating condition. The nose clip. Bearing in mind that this is a one-time use product. Everything's intact. You see the amount of soot residual on the canister itself. We wiped the hood clean, and that was also covered in soot. I'm going to separate it now. A little separating device. There's the filter. See, the filter has collected all these soot particulates, the micron-sized soot particulates, but it's collected soot residuals. There are no large soot particulates. You can see some larger ones in the bottom, but then in the fire there were no large soot particulates. None of the large soot particulates associated with polyvinyls, that sort of thing. Polyethylenes.
This part of the filtration device is also important. Is it the design of the canister?
Yeah. This is the inside of the outer canister, and it provides a large surface area for soot particulates to stick to. And you can indeed see some large soot deposits inside. This prevents the soot particulates getting to the filter and blocking it. Now you see that this filter is indeed black. That's because it's picked up the micron size soot particulates that it's supposed to have done. But you will notice.
And what color is this filter normally?
This filter is normally white.
It's normally white, isn't it?
You'll see that the desiccant, which is a very light color, is still very clean. So no soot particulates have got through to that. We're looking at the inside of the mouthpiece, the plenum area. You'll see that there are no soot deposits at all. It's perfectly clean. So no soot particulates got through the filter.
So nothing got,
The upper section of the filter is clean. No soot particulates got through there. Only on the bottom, where the electrostatically charged fiber filter, which is designed to collect the soot particulates, can you see evidence of collecting of
considering it's white, there was a fair bit caught.
That's right. Open up the filter. That's the filter retaining ring. Here is the fine stainless steel mesh, retaining mesh. This is the upper particulate filter. That colour on the bottom is caused by coming into contact with the hopcolite. That's not so. This is the hopcolite. You see it's still quite loose. It hasn't been compacted, so no signs of moisture there. It's quite easy to move around. So obviously no moisture has got through to it. This is the first retaining ring. Still in good shape, no signs of any effects of heat. Here is the second stainless steel mesh, quite clear, no deformity. Now we're looking at the molecular sieve. It's a material called zeolite. Quite clean. Any small deposits of any small black deposits are fines from the hopcolite. So we're going to keep that. As you can see, that's quite clean. Absolutely no signs of any soot particulates. We're now at the first stage. Just remove this sealing ring here. Again, no signs of effects of heat, no deformity. The last stainless steel separator and another fiber filter. This is a material called Filtrete, made by this darkening here, this marking is in fact as a consequence of coming into contact with the ASC carbon. They're not soot particulates. We're looking at the ASC carbon in the bottom here now. We're just going to push in. As you can see, it's not compacted. There's no signs of any moisture there whatsoever. It's quite loose. Just going to empty that in there. ASC activated carbon, military spec activated carbon. It has heavy deposits of metal oxides impregnated into the material to handle acid gases as well as Any other gas is typically found in a fire. You can see if you look inside there now, the inside of the lower filter, the outside is black where it's collected the micron-sized soot particulates. The inside is quite clear. See the difference there? Yes, it's slightly grey, but compared to the bottom, absolutely clear.
You got it.
Just removing the last sealing ring now. Again, no signs of any damage or deformity as a consequence of heat. There's the last fine stainless steel mesh, and here's the electrostatically charged fiber filter. Now if you look at that edge on, you'll see quite clearly the depth of penetration, about a 1/16 of an inch. No, maybe not that, a 32nd of an inch, just as an estimate. Around from the outside here, and it starts to go grey until it's relatively clear compared to the outside here. You can see the imprint of the wide mesh separator. So the filter is obviously well protected, and as you can see, because I'm still here, it operated very well. Let's take a look at the first line of defense here, the electrostatically charged fiber. Okay, let's cut through the electrostatically charged fiber filter. It shows a little more clearly the depth of. So here we are looking at a cross section of the electrostatically charged fiber filter, which in itself is about 1/8 of an inch thick in its cross-sectional depth. You can see that it still remains fully lofted. It hasn't been compacted, so the fibers are running vertically and in the most efficient format. You can see the penetration of the soot. This is on towards the outside of the filter, so the air carrying the soot particulates come around and hit the filter from this side. You can see the depth of penetration here to be about 1/32 of an inch, and the remaining is and then you have a slightly darker, lighter area. It's a sort of a dark grey instead of black of about 1/32, and the remaining much lighter grey area of about 1/16 of an inch. That tells us that this has done its job very efficiently. It hasn't been blocked. There are no large soot particulates on the surface here. They're all micron-sized pieces of soot. In fact, there we go. I'm just getting a little bit off there now. Now, of course, they'll be mixed with some fibers. So, that shows us that that filter worked very efficiently. It did its job as designed. This is very difficult to show because of the remains of the dust inside the canister. If we can clean that out a little bit, you'll see that there is soot residuals on the surface here. Not so much as on the inside as of the main canister. So all in all, the filter worked exceptionally well, and in fact in the test itself I could have probably gone on for at least another 5 minutes, possibly 10 minutes under those conditions without any ill effects.
Did you notice it harder to breathe as the test wore on, or was there really no?
No, there was no increase in no perceptible increase in pressure drop across the filter. None whatsoever. None that I could tell, or none that I could measure. It was most comfortable to breathe. Of course, with this type of product, with a negative pressure filter, you have to draw across the filter. You have to do some work in drawing the air across the filter, and that makes it a little more difficult to breathe than you would normally without any restriction whatsoever. But it has the effect of slowing your breathing down, which in turn calms you down. So there we have it, gentlemen. obviously a very successful test. And we're just going to take a look at the second hood that we used during the test. This was more for a sort of a replay for the media, but it was used in very dense smoke for a much shorter period. So let's take a look at this. Again, the Kapton hood. This material, as you know, is flame-proof and heat-resistant to way above anything the body can withstand. The wells and joints are sound and intact, no sign of failure. The exit from for the taping is slightly torn there, but has not failed. Bearing in mind that this is for one-time use only. It only has to perform once, and that's it. Take a look inside. The mouthpiece is intact. The inlet valve is intact, as are the exhaust valves. Nose clip still in full functioning order. We see the filter. It's very grey, which means it's picked up soot particulates immediately. The inside of this canister is much clean, but you might not be able to see it on the camera. I can see it with the naked eye. There are soot deposits around the surface area of the container. Excuse me. The electrostatically charged fibre filter is dark grey, which means it's picked up the millions of very fine micron-sized soot particulates that are drawn in with the air, and they've been trapped on the filter. Again, the zeolite, which is the light-coloured material, is quite clean. No signs of soot particulates getting through there. Let's take a look inside the plenum. The plenum is perfectly clean. Absolutely no soot particulates have got through the filter. The top of the filter, again, is as clean as it was made. There's the locking ring. There's the first stainless steel mesh. There's the first filter. That is dark on. Again, the hop collide is quite loose. There's no signs of it being compacted or affected by moisture. So it's obviously. Here we see the top surface of the zeolite, the molecular sieve, which has a twofold function. It collects moisture in order to protect the hop collite above it, and it also helps the activated carbon below it to collect and eliminate acid gases. Just going to take this locking ring out now. These locking rings make sure that each individual level of filter is isolated, and is isolated from the next section. There's the stainless steel wire mesh. There you see the surface of the zeolite. Granules are quite, the little spheres are quite loose. No signs of any soot particulates. Empty that into there. And as you can see, that's quite clean. This can be reused. We won't reuse it, but it can be reused. By heating it up and drying it out, it's as good as, almost as good as new. We wouldn't reuse that, of course. And there we have the surface of the next stage of activated carbon. What you're seeing there, in fact, is the separator, the stainless steel wire mesh, and behind that is another fibre filter, which is quite clean. There are no signs of that having been darkened by soot particulates. Here comes the locking ring, intact, in good shape. There is the stainless steel mesh. There is the fibre filter. Again, that darkness you see on the surface is just where it's come into contact with the activated carbon. The fibre itself is quite clean. There's the activated carbon. It's quite loose. Again, no signs of it been compacted with more. Here we have the military spec activated carbon. You see it's quite loose in there. No signs of moisture. It hasn't been compacted. Quite loose itself. Just deposit that in there. And we have the inside surface of the electrostatically charged fibre filter resting behind this stainless steel mesh. And we're just going to get those last few granules out of there. Let's see if we can't get that locking ring out. There it is. Locking ring is in good shape. Hasn't been deformed. There's the stainless steel mesh. And there's the fibre filter itself. Again, you can see the lines that have been pressed into there a little bit, where it's been protected. You see the clean white lines. You see the grey area where it's collected the micron-sized soot particulates, and the back side is quite clear. Again, the darkness that you see there is caused by contact with the activated carbon and the dust fines from that, the residual dust fines. So let's cut this in half and see what sort of shape it's in. Again, if you look at that, it's quite heavy collection of soot particulates here, very fine soot particulates. Much less than a micron, somewhere in the region of 0.5 to 0.3 of a micron. That's penetrated to a depth of about 1/16, maybe 3/32 of an inch. It's a little less here, about 1/32 of an inch. And then there's an intermediate area that's slightly darker, slightly lighter, sort of grey colour. And then we've got this white section here. Again, you can see that the full cross-sectional depth of the fibre has been maintained. It hasn't been crushed, and obviously was very effective. Again, that filter was operating perfectly and provided the level of protection that we anticipated. Thank you.
The interesting thing about this filter, as opposed to the other one, was the much higher levels of carbon monoxide experienced by yourself through the that the filter experienced. The much higher levels of carbon monoxide that the filter.
The soot particulates may have differed. There was more wood burning in the second fire, although we did burn wood in the first fire as well. In fact, the filter would be much more efficient at higher levels of carbon monoxide than lower levels of carbon monoxide. Okay. Of course, the catalyst becomes more effective when it's challenged by higher levels of carbon monoxide.
So, and by definition, a catalyst is something that's not used up in the reaction of the conversion of CO to CO2. So
that's correct.
So by passing carbon monoxide through, you're not using up any of the filter materials. You're just providing a mechanism to convert the carbon monoxide to carbon dioxide.
That's correct. It's an oxidizer. It would continue to work for a long time until it was slowly poisoned by moisture or acid gases that started to penetrate the first levels of the filter.
Oh, okay.
So the activated carbon would take care of the acid gases, as would, to some degree, the molecular sieve. The molecular sieve, in addition, would take care of any moisture that's in the air. So thereby, in a consolidated form, would protect the hot colite, the catalyst, in its operation, in its function, in its reaction.
And that concludes the live test of BrooksDale's EVACU8, an emergency self-rescue respirator. We thank you very much for taking the time to view the material and look forward to hearing from you in the future. Thank you.